The remarkable agreement between the observed abundances of these light elements in the universe today and the predictions of Big Bang nuclear synthesis is one of the strongest pillars of the Big Bang model. Throughout this entire plasma era, from the quark-gluon soup to the period of nuclear synthesis, the universe remained fundamentally opaque. Because electrons were not yet bound to atomic nuclei, they were free to move independently. Photons of light could not travel far without colliding with these free electrons. This constant interaction meant that the universe was like an incredibly dense fog or a thick soup of charged particles and light. Any light emitted would be immediately scattered or absorbed, keeping the universe in a state where it was impossible for light to propagate freely. This opacity is a key characteristic of the early universe plasma. The end of the plasma era and the transition to a transparent universe occurred approximately 38,000 years after the Big Bang. By this time, the universe had expanded and cooled significantly, reaching a temperature of about 3000 Kelvin, roughly the surface temperature of a cool star. At this critical temperature, the energy of the photons was no longer sufficient to keep hydrogen and helium nuclei ionized. Electrons could now combine with these nuclei to form stable, electrically neutral atoms of hydrogen and helium. This event is known as recombination, even though it was the first time these particles combined, not a recombination. Once the electrons were bound in neutral atoms, the photons were no longer constantly interacting with free charged particles. These photons were now free to travel across the universe unimpeded. This event is called photon decoupling, and the vast bath of these decoupled photons constitutes the cosmic microwave background CMB radiation.